I'm Bill Malone, reporting for the National Aeronautics and Space Administration. And this is Tilden Street, a quiet residential area in the northwest section of Washington, D.C. Morning in the nation's capital. And in this house, as usual, Marjorie Townsend is the first one at the breakfast table.
Good morning, Hattie. How are you?
Fine, and you?
Fine. Thank you.
But then quickly, the morning rush begins. Charles Jr., Chet, the oldest boy, age 12, deep thinker, scientific bent, 6th grade, major problem, spelling. Lewis, 10, can draw like a whiz. His problem, spelling. John, 9, good student, can spell. Richard, 6, named for a far-distant relative, Richard the Lion-Hearted. Decision on spelling, still pending. The man of the house, Dr. Charles Townsend, presently unavailable. Reason, his specialty, obstetrics.
Where's Dad? He just called from the hospital and said he was on his way home. He should be here most any minute. And I guess I better run. Bye-bye. I'll see you all this evening. Bye, Mom.
Hi, you made it home.
Morning. Sorry I didn't make it for breakfast. How are the children?
Bye.
You may think that the distance between that very domestic scene and something as far out as spacecraft is 1,000,000 miles. It's not. It's exactly 16.5 miles. For Mrs. Marjorie Townsend, wife, mother, has one additional title. She is a lead electronic engineer in the instrumentation branch, Aeronomy and Meteorology Division, Goddard Space Flight Center, National Aeronautics and Space Administration. She is one of the many thousands who are creating today the technology for tomorrow's satellites in space. Man's great adventure. The Goddard Space Flight Center, named to honor Dr. Robert H. Goddard, America's great rocket pioneer. Located on 550 acres of rolling land near Greenbelt, Maryland, the Goddard Space Flight Center is almost unique in the free world. Here, in this one complex, the full spectrum of space science is followed through. Experiments that will be placed aboard spacecraft are designed, built, and carefully tested. Goddard scientists and technicians supervise the launch of the spacecraft at various launching facilities. The Goddard-operated worldwide tracking networks follow the satellites in flight, receiving scientific data by telemetry, transferring the information to the computers at Goddard, where it is reduced into facts and figures, so that scientists can analyze the results of the spaceborne experiments. This is Building 11, one of the many laboratories at the Goddard Space Flight Center. It is here that Marjorie Townsend has her office. Getting the valuable data from the space laboratories is a job of the instrumentation branch and Marjorie Townsend. So her story is a story of telemetry systems, particularly one, her electronic baby, and its development. As one of the senior engineers at Goddard Space Flight Center, she supervises more than 30 electronic engineers and technicians. To get much of the detail work out of the way, she gets to her desk in Building 11 about half an hour early every day. Normally, this is routine, and a rather early routine it is, too, Mrs. Townsend.
It certainly is, Bill.
You know, there's a word that has come into our vocabulary through rather common usage, and I guess because of the wide coverage given the various space shots by radio and television. That word is telemetry. Now, can you tell me what it means?
Telemetry is the voice of the satellite, the communication link between the spacecraft and ground, very much like the radio receiver in your home picks up the signals that are transmitted, broadcasted by the radio station. Why don't I describe one of the telemetry systems that we used in Tyros?
Fine.
The Tyros satellite carries television cameras which take cloud cover pictures of the Earth. It also carries sensors to detect radiation. The sun radiates constantly. Some of this radiation is reflected by the Earth. Some of it is absorbed and emitted later. Both types of radiation, the reflected and the emitted, are picked up by a sensor on the outside of the Tyros spacecraft.
Right.
The job of the telemetry system is to get this radiation information back to the ground.
And this is heat radiation we're speaking about.
That's right. The telemetry system begins then with an oscillator. The oscillator puts out a wave that looks very much like this, sinusoidal type of pattern. The signal from the sensor modulates this oscillator so that we change this frequency. We either increase the frequency so that the waves come closer together or decrease it so that they come further apart. Now, it takes an hour and a half for the spacecraft to orbit the Earth, and we have to store the information because we don't have continuous access to the ground stations.
Now, this is collecting this information all the time it is orbiting, this
Right,
Tyros.
continuously. So we store it on a tape recorder which flies in the spacecraft.
Right.
It stores the data for an hour and a half. As it passes over the ground station, as Tyros passes over its ground station, that is, we command this into playback. We speed it up by a factor of 30 so that that data, which we stored for an hour and a half, we can play back over the ground station in 3 1/3 minutes.
Actually, it took us an hour and a half to collect this data, but only 3.5 minutes to actually play it back.
Right you are. Now, we play it back, of course, through a transmitter. And this transmitter is modulated by this signal, very much the same way the sensor modulated this oscillator.
I see.
The signal then is transmitted to the ground.
Right.
This part of the telemetry system is in the spacecraft.
All of this.
All of this orbiting the Earth continuously. Down on the ground, then, we have a receiver, very similar to the radio receiver in your home.
Right.
This receives the signal from the spacecraft.
Right.
And the output of the receiver has a signal which is just like the output of the tape recorder was up here.
I see.
The next step, then, is to demodulate this signal. And the output of the demodulator, when we finish, is just like the sensor signal that modulated the oscillator.
Which was the originally collected signal.
Right. Now, we have here the telemetry system, the block diagrams that you see on the board. But I'd like to go on and explain just a little bit further what we do in the ground processing, because we have so much data that it's hard to handle it without using a computer. So first, we convert this into computer language. Then we can feed it right into the one of the large-scale computers that we have at Goddard. And the output of this is a map of the Earth's radiation.
So this actually map is as you say, the Earth's radiation pattern as was originally collected by the sensor orbiting the Earth. And I suppose that's why we put it up there in the first place, to get this information.
Yes, to get the overall view.
I see. Now, is this what we have referred to as your baby?
No, this is the telemetry system that preceded that. The development of that system is a story that began some time ago. I remember it was a Friday, and we were just about ready to close up shop for the weekend when Dr. Rudolf Stomfel, the head of our branch, gave us the news.
We have decided not to fly the radiation measurement experiment on the first Nimbus weather satellite. That means that we have lots of time now to do the things that we always wanted to do, but couldn't because of the pressure of time. The equipment did a good job in the Tower spacecraft. It could do a good job on the more advanced Nimbus weather satellite. But now we can revise the whole instrument package to get more accurate information more reliably. You say you enjoy problems. Here's a good one for you to solve.
It certainly is.
And now, have a nice weekend.
Dr. Stamfel had underlined the challenge. There was now time to revise the entire telemetry system for the Nimbus radiation experiment. The goal, to obtain more accurate information, greater reliability. Mrs. Townsend and her associates accepted the challenge.
I remember when I discussed moving from my job at the Naval Research Laboratory to Goddard. My husband wondered why I would give up more than 8 years of pleasant, interesting work to start all over in a new setting with new people, working with a phase of electronics that was new to me. It was a difficult decision, but one I've never regretted. The work at the Goddard Space Flight Center is always challenging, always exciting, with each day more fascinating than the last.
The written language of the electronics engineer resembles the hieroglyphics of the ancient Egyptians, and to most poor mortals is just as puzzling. The hieroglyphic is a picture representing an idea or a word, a circuit of intelligence between the writer and the reader. The diagrams of the engineer are also representations. They chart the flow of electric current through a system of transistors and gates that control it. Store it. Turn it on. Turn it off. Logic diagrams. Circuit schematics. The paper tools of the electronics engineer. With these, Mrs. Townsend worked on the system concept, developed her plans. Then one day her plans were complete.
All right, Rudy, here's what I want to do. If we take the converter out of the ground station, put it up in the satellite, then we can convert from analog to digital form right up in the bird. We can record on 8 digital tracks of the 1/4-inch tape. When we play back as it passes over the ground station, we can do it very fast. The signal that's transmitted then will not be affected by any noise in the atmosphere or in the tape recorder. We should be able to improve our accuracy by a factor of 5.
Well, what about the variations in tape speed? You know this is always the problem. How do you propose to handle this?
I knew you'd ask about that. It was
This
a
is the
problem
marvel
I
of
kept me up
Goddard.
at night for
People
quite a
with
while, but I
ideas,
think I
new,
finally
provocative
solved it.
concepts,
If we
breakthroughs,
record our
good
digital
ideas
tape
that somehow don't work out,
on 7 of the
strange
tracks,
ideas that suddenly take fire. But before the good turns bad, or the strange proves good, the opportunity to test, to try, to prove. At Goddard, engineers and technicians have the finest, the most modern facilities to work with. But even more important, far more important, is the human measure. The constant flow of imagination and impulse that makes this place the laboratory of space science. And at Goddard, science is the great equalizer. It's not who you are, but how you think, how you tackle a problem, sweat it out, and find an answer.
It's all laid out in my proposal.
Sounds good, but the only way you will get all these components into the spacecraft will be by using microelectronics, at least for the logic circuitry.
That's exactly what I had in mind.
Well, then let's go and do it.
All right, we will.
Logic circuitry, microelectronics, a marvel of engineering which, one day soon, will give you a radio the size of a $50 and a TV set the size of a pack of cigarettes. This is a conventional tube circuit, the type you'll find in most TV sets today. This is the same circuit using transistors instead of tubes. And this is the same circuit using microelectronics. In this tiny module are transistors, resistors, capacitors, diodes, all assembled under a microscope. Miniature, but not a toy. Tough, reliable. This is the logic circuitry Mrs. Townsend will work with. Not alone, of course, for once Dr. Stample gave the go-ahead, personnel and facilities in the instrumentation branch were made available for the project. One of the first engineers to be called was Paul Feinberg. After many a conference, many a working session, the concept got down on paper, a logic design, showing how the microelectronic building blocks might be used to produce the signals and timing required, and still withstand the stresses of spaceflight. And there were other problems, too.
Can you tell
Problems
me
like
how the
this.
tape drive works?
Well, Marge, we use the endless loop version on this recorder here. And this works, the tape comes off the inside diameter or the hub of the tape reel and goes by the heads and back around and back onto the tape cartridge on the outside diameter.
I see, and the tape's lubricated then so it won't stick as it goes.
Yes, it is. It's lubricated on one side and has a magnetic oxide on the other, which is used for recording.
Where were the heads again, the 8-track digital head?
The 8-track digital head is located here at this point.
Well, this is the problem that we have now. We have some amplifiers, Ed. Where are the amplifiers? We have 8 record and 8 playback amplifiers that we have to put on with this head now.
Well, Marge, I think we can. There's a possibility that we can put it down in the bottom part of our container here. The recorder has this top plate, as you can see, and then there's a lower plate down in the can, and I believe there's room that we can put it. It will take some investigation.
Are we going to have any trouble with the harness, Ed?
No, there shouldn't be a harness problem. And actually, we can't get this any smaller, so this has got to go.
The problem is a familiar one to space-age scientists and engineers. The necessity of fitting as much gear with the least amount of weight into the smallest possible area. Mrs. Townsend and her colleagues have been allotted only a small portion of the space inside the Nimbus satellite. They must fit all components of the radiation experiment's revised telemetry system into this one area, making the most effective use of the available space. The creation of microelectronics has made this job conceivable, but the final, practical design will depend on human judgment, the pooling of knowledge and ideas, and the check and balance system which will ultimately lead to the solution.
To get it inside, if it's at all possible. How many other things are there under here besides that?
Well, we have the playback mechanism on this plate. It's on the bottom. And I think that there should be room over here on this left corner underneath. There is some electronics under there now, and I think that we can. There's a good chance.
All right, well, I guess the thing to do is take it in the lab and take it apart, see if we can get it in. We also have to hook the amplifiers up with the head to make sure that works. Now, how soon do you think we can get that done? Do you have any time schedule in mind, Ed? Think we can do it tomorrow?
I think this is possible. I'd like to look at another approach here, too, and this is integrating the amplifiers with the base of the transport. This would cut our cabling problems down tremendously. Shorter leads.
And this is a possibility, too, but they're really, if you want to put it onto this plate, that's what you're saying.
Well, looking at it from the electronic side, of course, I see a space down there.
Well, that's true, but
it would be good if we could do it.
Yeah, but see, there's this cutout here is to provide clearance for a little timer box that we have in the tape recorder, and it would be pretty hard to put it on this plate. I think that we better try and mount it on the lower plate rather than this piece.
We can change the configuration of this box, can't we?
Yes. Yes.
All right,
we could make it
consider that thinner and longer, but the volume would stay the same. Well, let's take a look at it and think about it some more and maybe get back together next week and see if we've worked out the problem.
Okay.
It's okay by you.
Okay, thanks a lot. Appreciate it.
And so the work progressed. This is the breadboard, not the configuration that will actually be used, but the bringing together of the hardware, applying the power, and checking out the system under conditions of extreme heat and cold that approximate the temperatures of outer space.
Paul, I'm going to hook up this resistor and see if this makes any difference.
Meanwhile, another member of the engineering team, John Lesko,
See what
worked
that
up the
does on the
design of a
scope.
ground station to receive the telemetry from the
Looks okay.
spacecraft.
Sure does. If we've got a good... Oh,
Uh-oh. Did you touch anything in the ground station, John?
Time and again, things went wrong.
Okay.
One way failed. They tried another.
They seem to be working
yeah.
all right.
Must be in the oscillator.
See if you can fix it.
Improvisation, a little guesswork, but a lot of know-how. And somehow, the kinks got ironed out.
That did it. Looks fine now.
Real good.
Months crowded in so quickly now, it's hard to separate one from the other. We built a pre-prototype model of our little black box right here in the laboratory. Then we shipped our mechanical and electronic drawings to the company under contract to build the actual flight hardware. Then came the day they sent us their first production unit. I remember how Paul, John, and I hovered over it, examining every inch. This was our baby. Especially nice to have up front so we can look at it. It's a good thing this thing works.
Well, I'm glad to see you have it in. When do you think we can get it over to our test and evaluation people?
They're ready for us now.
Well, good.
It's a paradox, but spacecraft meant to roam the heavens must first survive the tortures of hell. The Goddard Test and Evaluation Division is dedicated to the proposition that everything space can do, man can do better, or worse, depending on the viewpoint. The vacuum thermal chambers simulate all the extremes of space. Almost a total vacuum, extreme cold, extreme heat. In the dynamic test chamber, all these conditions are duplicated for the spacecraft and its subsystems. Subsystems, alone or in combination with others, are subject to terrific vibration, up to 2,000 cycles a second, simulating the rocket that launches the spacecraft. The last test, the centrifuge, where the system was accelerated to G-forces exceeding those which it will encounter in the spacecraft. And so the system test was completed successfully. And so with this happy result, I presume your work on this project is ended.
No, that's just the end of phase one. Now we have to put this system into the Nimbus spacecraft to make sure it works compatibly with the other systems.
You mean after all these tests that you have conducted with this system, you still have a whole new series of tests to conduct with the spacecraft itself?
You bet we do. We want to make sure it works when we get it up there in orbit.
That's a mighty good idea. Now, we'll be up there in orbit in the Nimbus spacecraft, and this is a new spacecraft. What are the refinements or the superiorities of this Nimbus spacecraft?
Well, Nimbus is a more sophisticated meteorological satellite. Instead of pictures of only selected areas of the Earth, it will provide continuous television coverage of the entire Earth's surface. In addition to that, it has better radiation experiments for mapping the cloud cover at night.
So this, then, is Nimbus.
Yes, it is.
Thank you, Mrs. Townsend. Someday, not too far away now, a Nimbus weather spacecraft will be hurtling around the globe in a pole-to-pole orbit, carrying a very important box of electronic circuitry. As the satellite passes over the ground stations miles below, this telemetry system will chatter out its message about the Earth's radiation, while other telemetry systems in the spacecraft will transmit television pictures of the Earth's cloud cover. Clear, reliable information that meteorologists can translate into weather forecasts that someday will tell the farmer in Iowa when he can expect rain, the seaman in the mid-Pacific that a typhoon is in his path, the vintner in France when to gather his grapes. By that time, Mrs. Marjorie Townsend and her colleagues at the Goddard Space Flight Center will be well ahead on advanced concepts of spacecraft telemetry. For this adventure, like space itself, is infinite without end.